Hi, I'm Rodolphe Lepigre, and on behalf of all my co-authors, I'm going to present VIP, which is a step towards the verification of real-world systems C code. There are loads of challenges, so instead of trying to verify arbitrary systems code, we focus on code involving integer pointer casts, as systems code relies on them and they have particularly tricky semantics. An example of use of integer pointer casts is pointer tagging, which consists in writing metadata in otherwise unused bits of pointers. And here is what a typical tagging function looks like. It takes as argument a pointer p that may already have a tag, and a new tag value t to apply to it. The function then starts by casting p into an integer I, and then the tag is written using integer arithmetic and the result is stored in variable new I. And finally, new I is cast into the result pointer q. So what we have seen here is that the tag function relies on the fact that pointers are not just abstract values, but also have an integer representation that can be manipulated. Hence, in order to verify such code, we first need to answer a big question. What is the semantics of pointers and integer pointer casts? Although this question may sound simple, the design of a memory object model is an active research area. The main reason why integer pointer casts are complicated is that there is a tension between a concrete and an abstract view of pointers. In a fully concrete model, where pointers are represented as simple integers, integer pointer casts are trivial identity functions. However, such a model is not sound with many optimizations performed by compilers like GCC or Clang. Dually, in a completely abstract model, where pointers are abstract entities, many standard optimizations are justified, but code like our pointer tagging function is not supported. So, in a way, the concrete model is too concrete, the abstract model is too abstract, and what we want is something in the middle that is just right. And that's what we've called a Goldilocks memory model. In fact, there has already been quite a bit of previous work on the design of such Goldilocks models, and amongst them is PNVI-ae-udi, or PNVI for short, and that is the model upon which our work is built. So, if PNVI is already one of these nice Goldilocks models, why not just take the paper where it is described, implement it in a program verification framework, and get done with it? After all, PNVI is a pretty good model. It has been substantially validated against not only the C standard, but also de facto practices when they happen to diverge from it. It is also mostly compatible with optimizing compilers like GCC or Clang, and it might even become part of the C standard in the future. Or at least, it is currently the preferred option. So the downside of PNVI, on the other hand, is that in order to do all these good things, it needs to just work for a lot of existing C code, and as a consequence, the model is very complex. For instance, PNVI has to deal with integer-to-pointer casts for pointers whose address points both at the start of an allocation and one past the end of another, and it does so by tracking both possible provenances at once until a choice becomes necessary. So overall, PNVI is not directly suitable for verification, or at least it is unappealing due to its complexity. However, since there are lots of good things for PNVI, what we ask ourselves is, how can we build a verification tool atop PNVI anyway? So what we've done in this work is design a new memory object model called VIP, which is targeted at verification. And in particular, it is much simpler than PNVI. To demonstrate that VIP is suitable for verification, we have extended the RefinedC verification framework to use VIP, and we verified a number of integer pointer cast idioms using it. Moreover, what is great about VIP is that it is compatible with PNVI, in the sense that whenever a program has undefined behavior under PNVI, it also does under VIP. As a consequence, we proved a theorem stating that when a program has been verified under our version of RefinedC based on VIP, it does not exhibit undefined behavior when executed under PNVI. What this means at a higher level is that, at least as far as the memory object model is concerned, a program that has been verified with RefinedC can be compiled with GCC or Clang with some guarantee that it will not go wrong. Now, to conclude, let me quickly explain the key idea of VIP, which is to require the programmer to annotate integer-to-pointer casts with a provenance. Intuitively, a pointer's provenance identifies a corresponding allocation, and in both PNVI and VIP, pointer provenance is exactly what enforces that the model is abstract enough to support compiler optimizations. Going back to a pointer tagging function, we can make two observations. First, the argument pointer p comes with a provenance, but provenance is not propagated via the integer arithmetic. And second, when new I is cast into a pointer q, a provenance needs to be constructed for it. And clearly, tagging a pointer should preserve its provenance, so q should be given the same provenance as p. However, this is not at all obvious to PNVI, and in some cases it may need to work with an ambiguous provenance. To avoid all ambiguities, VIP requires replacing the bare integer-to-pointer cast with the use of a specific copy allocate instruction. And this instruction performs a cast but additionally assigns the provenance of its second argument to the obtained pointer. And thanks to this idea, VIP can easily be integrated into a verification framework like RefinedC that can then be used to verify functions like tag. Thanks for your attention, and if you want to hear more, come and see our long talk.